Hi, and welcome to the February edition of According to Pete. Gonna take a break from my project that I've been doing to talk about some of the questions that are in the queue. There's a lot of questions in the queue. Shorter questions, so we were able to get through like 4 of them, I think, in the course of this episode. So the first question we're gonna do this time, it comes to us from a Mr. or Mrs. X, because there was no name attached to the spreadsheet that I was looking at. Mr. or Mrs. X asks, how did I pick the 2 resistor values to set up the reference voltage on the op-amp example I gave so many months ago? So let's talk about that, and let's go to the board. I've got an op-amp that I'm operating on a single polar supply. I got VCC, I got ground, okay? In order for this thing to have a linear output, I want the output to be situated at its quiescent point, where it's not doing anything, halfway between the supply voltage and ground. So in order to get that, you put that voltage on the non-inverting input, right? So that's what I've done here. Now back in the day, I set this up somewhat arbitrarily, as I recall. Somebody go back and check and see if I'm lying. I set this up with 10K resistors and sort of disregard that jumper over that. This is the other reference setting resistor, and it was 10K, okay? And I think at the time I said, select something between 10K and 100K and you should be just fine. But why? Why I select these values to be 10K is because you're also calculating the input impedance in parallel with this guy, the input impedance of this pin, right? So what you've actually got is like another resistor there to ground. So we're calculating what this voltage value is going to be. And the real equation, like the way it's normally calculated is, and I'll call this like Vref, all right? Vref equals VCC times R2, which is that guy, over R1 plus R2, all right? And this is obvious for anybody who's ever seen anything like Ohm's law, right? Okay, and most of you will get this too. Some of you may not. But the actual equation is not this. It's very close to this, except that the term R2 actually becomes R2 in parallel with question mark ohm, okay? So your Vref can change based on what this value is. This value is supposed to be arbitrarily high. If you look in a data sheet, sometimes they won't even tell you what the value is because it's so astronomically high or something like that. But it's supposed to be so high that it doesn't really matter what you choose out here, okay? And you can see that. I mean, anybody who's done this equation, parallel product over sum, knows that as this value goes arbitrarily high, it's just R2 that we're concerned with. And for the most part, that is the case. With that being arbitrarily high, like I say, you can pretty much make these anything you want, okay? Really cool for a battery-operated application, because you can make these really, really big, and you're not going to have to worry about that parallel resistance, right? So why do I go with values between 10 and 100K? Well, let's see. First of all, I don't necessarily believe what data sheets tell me sometimes with regard to CYA specs, as it were, and I'll let you guys figure out what CYA means. Marketers do that. The second thing is, I like to, very, very small currents, like if I jack these values up to like 1 meg or something like that, much less current flowing through this guy, okay? That kind of thing becomes susceptible to noise. And this is a really high gain, right? So this is still our op amp, and you're still going into the plus input there. Really high gain, very small current, very small amount of noise can start to jack with your stuff. Now, it could be argued, of course, that you're going to be putting, you know, something down there to filter that noise anyway. So, okay, fine. I get that. Now, if you increase these values dramatically by orders of magnitude, like in the meg range, in theory this will all work, but something else you've got to take into consideration, and I generally don't, but something you're supposed to take into consideration, is that the impedance at this point, going into this input, is supposed to match the impedance seen by this point, the inverting input, okay? And the reason for that is it's supposed to minimize your input offset voltage, which can jack up your output too. So if you've got, 10 megs out here and you've got a gain of 10, then that's a 10 meg, and that's 100 meg. So very, very small current. I would expect this thing to maybe get a little sensitive to noise and stuff. So you'd have to decouple this circuit at least a little bit carefully. But as a rule of thumb, I do the two things. Number one, I do put this cap here. Number two, I keep my values much lower than the impedances that are gonna start to jack with me, like 10 megs or something. So I've got a current big enough here to swamp out noise, and I've got a cap here that's gonna further get rid of the noise, and I've got values here that are running enough current that I'm never gonna have to worry about it. So it's a couple of rules of thumb that I stick to. Honestly, I've never had to worry about input offset. As long as you've got like your impedances within the same order of magnitude. And remember, like the impedance of this pin is like these two resistances to ground, right? Because they're in parallel with respect to ground. And the impedance seen at this point is like this one to ground and that one to ground as well. But as long as you're in the same order of magnitude, I don't think you're going to have too much difficulty. Your offset might be a little bit depending on the gain, but if you stay like a gain of 10 and you're in the same order of magnitude for impedances, I don't think you're going to have too much to worry about, though somebody may totally stomp on me in the comment section, and hey, welcome to it. But there you go. That's how I choose these values. I like to keep them low. I like to have enough current to swamp out noise, assuming that actually works. I think it does. And that's it, I believe. And that is op amps, quicker and dirtier. The next question comes from Carl. Carl asks, why when you drive an LED from a microcontroller pin that you more often see a configuration of a low-going pin to pull current from the LED and light it up than a high-going pin from the microcontroller to source current to the LED. Why is that? Just so we're all on the same page, let me draw a picture. So what Carl says is, why do you see this configuration more often than this configuration? Okay, and pretend this is a microcontroller, because it's not. And this guy, right, I've got this voltage tied high, and I do a low going signal to turn LED on, which educators say is counterintuitive. They're right. Whereas this one, you drive it with a high voltage, LED turns on, okay? So why do you see this one more often than you see this one? And Carl speculates, well, a little more than speculation. He did some homework, it seems, that this is a holdover from older TTL technology versus CMOS technology. Saying that TTL devices have a harder time sourcing current than they do sinking current. Sinking goes to ground, sourcing comes from positive voltage, or negative voltage. And from what I can tell after doing a little bit of legwork is he's right. It is a holdover from that technology transition. However, I'd like to put a little bit of spin on it of my own. Oh, and by the way, there have been a couple of questions as to why you put the LED here and why you put the limiting resistor at the top or the bottom. Doesn't make any difference. You can put it here, you can put it here, you can swap them around, you can give them names and faces. Doesn't matter. It's a series circuit. The current here is the same as the current here is the same as the current here. As long as the cathode goes to ground, right, you're golden. So don't worry about that. Now, for my take, I still do this, right? I understand that CMOS is just fine sourcing current. But I still do this, and the reason I do this is because if I'm doing it this way, I can only supply. I've got to supply the differential from ground, okay? And for any given microcontroller, this is probably going to be like less than 5 volts, probably 3.3, maybe less than that, okay? So not a whole lot. Whereas if I'm doing this, I'm just supplying ground, and that's easy. I don't have to make huge voltage. And I can tie this to whatever I want, right? I can tie it to the 3.3, I can tie it to 5, I can tie it to raw voltage somewhere else, off a battery, off my car battery or what have you. You know, it makes me feel like my circuit's just a little more versatile, and I can change it up a little more if I have to, and I'm not going to be restricted to just that 5 volts. Does that make me feel free and easy, like I'm walking through the meadows? Yes, it does. It allows my designs to be a little more versatile, I think. Although it could be argued that if you're going to be working with a higher voltage, odds are you're going to be working with a higher current. You probably want to be switching that out with a transistor or something, possibly. But nonetheless, I like to stick to switching out ground. That's my fave. That's my convenience. That's my convention, and I'm going to stick to it. Next question comes from Brian, who asks, how much does the average hobbyist have to worry about electrostatic discharge? Meaning, can I walk across my carpet with my parts in my bare hands and not have to worry about destroying them? SparkFun production downstairs takes ESD pretty seriously, right? As any production house would. You don't want to be throwing money down the drain needlessly through being careless. And you don't want to throw, you know, unknown problems into the mix when you've got X thousands of boards to test. With regard to my own projects, I have never taken any precaution personally with my own projects with regard to ESD. Not once. I work on a wooden bench. I got carpet on the floor. I don't have a static mat. I don't have the thing around my cuff to keep. I don't bother with any of that. I have certainly burned a few parts through negligence or cruelty or just the will to cause havoc. But to my recollection, none of them have been destroyed through ESD. And any time where I thought ESD might have been a culprit, it's ended up being pilot error of some kind. Do I advocate this? No, of course not. For all I know, I've got a superpower that keeps ESD away from me. So I wouldn't worry about it too much. I'd certainly keep it in mind if you've got expensive parts, but I wouldn't really go investing in a clean room. So your mileage may vary, but there you are. Last question. Here we are. This one comes from Joe X. Joe apparently dug my workbenches in my garage. And he asks me if I've got plans for those or drawings or something. Oh, no, I don't. It was a very simple matter. I figured out how tall I wanted it, figured out how long I wanted it, went to Home Depot and measured what a 2x4 actually is, because it's not 2x4. I figured out how much wood I needed, bought it all from Home Depot, brought it home, started screwing it together. Very low tech. But what I can tell you is that the impact driver I got for doing this project is like the coolest tool in the world. If Thor did not have a hammer, this would be what he'd go into battle with, right? An impact driver from Home Depot. And in case you're curious about an impact driver I got from Home Depot, the model number is R86034K. So that's it for the February edition of According to Pete. Thanks for watching, as always. Keep the questions coming. You can put them in the comment section down below, or you can email them to feedback@sparkfun.com with According to Pete in the subject line, and they'll get put in the queue, and I'll look at them and say something moderately intelligent, maybe. So thanks, and see you next month.